Coastline of Norway and the United Kingdom.
The coastline of Norway. Well, that was not expected. I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class and your creation. Just pray that you'd help us to understand just a little bit more about it today, Lord. In your name I pray, Lord Jesus. Amen. So today, this is not lecture 10. This is actually lecture 40, but I'm recycling, all right? And this is a lecture I wrote on classical field theory for my general relativity course, but it applies here, all right? So the basic issue is generalizing the Lagrangian formalism for several variables, right? You typically talk about, Euler-Lagrange equations with respect to everything being, in classical mechanics, everything's parameterized with respect to that universal Newtonian time, right? He's not gotten away from that yet, has he? There's still time in classical mechanics that you guys are doing, right?
Yeah, he's
That hasn't gotten swallowed up in the phase space yet, has it? No.
Oh yeah, that has.
Oh, it has. Okay. All right. Well, yeah. Anyway, so if we think about space-time, well, then space and time are both, parameters for our fields. Our fields are functions of both space and time, and so when we need to adopt the variational principle which reflects that reality. It's not just all in terms of time. And so here you're looking at a Lagrangian density which depends on some fields, which I've denoted phi sub I, upper I rather, and their space-time derivatives, right? And we're integrating. That's the Lagrangian is this. This is the Lagrangian density, and if you integrate the Lagrangian over time, that gives you the action, right? And then, as usual, we suppose that the variation of the action, the principle of least action, that should be 0. We think that that's going to give us the equations of motions. It's sort of a general physical principle, which I don't motivate. I just assume is basic, which apparently doesn't have to be basic, right? But anyway, so taking the variation of this, there are, derivatives with respect to the fields and also derivatives with respect to the derivatives of the fields. And we take both the fields and their derivatives as independent variables in this formalism, which is always a little bit off-putting when you first see it, right? Because how can it be that this and that are independent? We also face this with the regular Lagrangian mechanics, right? How can you take Q and Q dot to be independent? What does that mean, right? Because Q dot definitely depends on Q. It's the derivative of Q. So how are those independent? So the answer lies in the fact that you're really doing some mathematics, which is you're introducing new variables to decouple the meaning of variables that you're given. You're working on something called the jet space. But anyway, that's a mathematical way of formalizing the fact that when you differentiate with respect to Q and Q dot, you can tell the difference, Anyway, so the usual song and dance here, we vary the action. We've got these two kinds of partial derivatives, but then you do the product rule here, right? And when you do that, unproduct rule, right? Integration by parts, other people would say. Then you get this piece, which we assume goes to 0 because it's a total. It's like a, it's a total derivative, so that integrates out to 0. Because we assume that the variation of the fields is 0 on the edge of the space-time region we're setting this thing up with, and lo and behold, we're left with this, and that must vanish because this has to be 0 for arbitrary variations of the field. Consequently, we get the Euler-Lagrange equations, being that these vanish. But be wise. Here, there's a summation over mu implied. This is using the Einstein. Let me see if I can turn off the lights in here a little better. This is using the Einstein, summation notation here. This is a sum over space and time. Mu equals, 0 to 3, like we've talked about. So that is the Euler-Lagrange equations for fields in space-time. We have to calculate the partial with respect to the I field, and then, that is equal to minus the, time. And basically, this is like the four-dimensional. It's like sort of a four-dimensional divergence, but not exactly, right? It is what it is. Here's an example. You can talk about a real scalar field. That would be something you could use to model, for example, a neutral pi meson. It has kinetic energy term 1/2 phi dot squared gradient energy this, potential energy that. I mean, this is being a little bit vague here. This is some sort of like phenomenological model that describes the pi meson. Don't ask me for the formula for V sub phi. I don't know it. You could propose different ones and see what that means, but anyway, like how you actually implement that summation. Notice that there's like an upper and a lower, it's a covariant contravariant index. So enter, this is the G mu nu we talked about. This is the Minkowski metric. It's -1 for 0, 0, and it's 1 for the off. It's diagonal, and it's only -1 for 0, 0. It's 1 for 1, 1, 2, 2, 3, 3. So this only gives us non-trivial when we've got like time, time, right? So when you have time and time, each one of these just becomes a derivative with respect to time, which we use phi dot for. So that's why we have phi dot squared here. That minus cancels with a minus. There's also, oh, the half is still there. Okay, good. And then of course, also over here, you have like, you know, x, so the x derivative, and then the y derivative, and the z derivative. Altogether, though, that's the product of like the gradient dot product with itself, right? So that's that term. And so in total, the Lagrangian, which for the, again, for the real scalar field is that, gives us the following equations of motion. We have partial L partial phi is minus, let's see here. So the only phi dependence is in the potential, right? So partial L partial phi is that, whereas this derivative, so this takes a little bit of, you know, what's the word? I mean, I'm differentiating a product here, right? So that's why I have a product rule. And then what I'm doing is, so this is only, what we mean by partial derivative with respect, I mean, whatever we mean by the partial derivative with respect to the derivative of the field, it must be that these are independent variables, right? So that, in a nutshell, means that this is 1 when they match and it's 0 otherwise, which is contained in that Kronecker delta and the other one. And then, of course, basically, if you knew a lot less and you just did this sort of like heuristically, you'd be like, oh, it's a square, so it just differentiates to twice itself, right? And that is what happens. If you like just kind of get past the contraction details and everything, we're differentiating this, which you might just write as like a square. Some people would just write like, you know, partial mu squared or something, and it differentiates to twice partial mu. And the half goes away. So it really, the calculus is more forgiving than you might think. Because I was doing all this and then talking to my friend in grad school, Manuela, and Manuela was like, it's just, you know, the square differentiates to twice the thing. And I'm like, yes, that's true for all these reasons. But she was, of course, content to just, you know, calculate as it had been intended. I'm going to go close that door. It's distracting me. All right. So, let's see here. So the Lagrange equations for this real scalar field problem, we just have, as after we get through all the details, it's just this is the equation of motion for the real scalar field, which, by the way, this is that del inversion we talked about before. It's the contraction of the space-time derivatives against themselves. That's what we call box, or I think box squared in Griffiths, right? It's the four-dimensional gradient. And these right here have a name. I'm trying to remember what they are. It's nameless at the moment. I mean, that's the del inversion, sure, but oh yes, this is the if we put in the particular context of putting, you know, there's like nobody in this whole floor and they're talking outside this room. Like, what in the world? Go away. Just go. Skedaddle. Anyway, shut up. Sorry, they can't hear me thinking. So with this particular, if we assume the potential is like that of a simple harmonic oscillator, then this becomes the so-called Klein-Gordon equation, all right? And I think if I remember some of the reading I was doing, I was trying to read some on some of these arguments, and I think I read some things like this equation maybe is not actually that physical in terms of like it's got some very undesirable properties and so forth. But it's one of the basic toy models of classical field theory people look at, and it is, you'd like to understand it more if you're going to become a theoretical physicist at some point, but anyway. So what I wanted to mostly talk about today, of course, was electromagnetism from the Lagrangian formalism. And so this is actually section 1.10 in Sean Carroll's General Relativity book, but, thought I should do it with you guys. So as we've talked about, you've got the one-form potential, right? Here phi is the voltage, all right? We use V, you use phi. And I think here C has been set equal to 1, so don't look for dimensional consistency with the things we've done in that regard. Of course, we define the field tensor, as the anti-symmetrization of the, anti-symmetrized derivatives of the one-form potential. And we, as we talked about this semester, we got that gauge freedom. If we shift this to, plus a space-time derivative of a function, we still get the same field tensor. It's gauge invariant. And seriously, just I think they're maintenance or something. Anyway, talking about a crack in the floor or something. All right, anyway. So we talked about this a little bit. Like this is just a notation for that. I called it the Bianchi identity, right? The sum of the derivatives. And like you go through the cyclic permutations of the mu, the nu, the sigma. And that gave us the homogeneous Maxwell's equations, right? Whereas, as we talked about, so here's all that again. Of course, it's even easier to see the gauge symmetry if we use differential forms because it's just d squared being 0. Then you have the Hodge duality to get you over to the corresponding dual tensor, and lo and behold, I'm trying to find the silly equation. So this, of course, the exterior derivative of the Hodge dual of the field tensor being the Hodge dual of the current one form. This is the inhomogeneous Maxwell equations, right? Gauss's law and Ampere's law with Maxwell's corrections are both in here. Technically speaking, this is called a co-derivative, by the way. Maybe I might have to Hodge dual again, but like you can play a game with Hodge duals in the exterior derivative to decrease rather than increase form degree. Like the exterior derivative, it goes p to p plus 1. This co-derivative goes p to p minus 1. So like there's a way of looking at Griffith's dual equation. I don't know. There's about 15, it's like a half a dozen different ways to set these things up.
We did it last semester too.
Oh, I did? Okay, cool. I can't remember. I never remember what I did with you guys, but
We used delta for it is what we did.
oh, right. I did have that homework problem today. Thank you for reminding me. So, lo and behold, this is the Lagrangian for electromagnetism. We have the contraction of the field tensor covariant and contravariant like that. And then also the contraction of the one form against the current. So this couples the gauge field to the current. This is a coupling term. In the modified problem I gave you, there's also a mass term that I added that it couples the gauge potential to itself. I think if I remember right, well, let's just look at it for a second. If I can find it. Yeah. See, so the difference, so what we're looking at right now it's just got this and that, right? In your homework, I added one other term over here. So the way to do this problem is very similar to what I'm about to show you. It's just you also have to take partial derivatives with respect to this. Now this is essentially like a simple harmonic oscillator term for the gauge field. It's analogous to like that 1/2 m phi squared term we looked at for the real potential. What it's doing is it's giving mass to the photon. So it's, you're not going to get Maxwell's equations. You're going to get something else. They're called the Praka equations, if I remember right. So, wait a minute, what? Oh, there we go. I was like, why did it take me back a page? That's weird. Anyway, okay, so to set up the Euler-Lagrange equations here, we simply have to take the partial derivative of the Lagrangian with respect to the potential. And when you do that, you notice that the field tensor only has like derivatives of the potential, right? So those are independent from the potential in this formalism. Just like Q is independent from Q dot in your classical mechanics, right? So when I take partial A nu, it only picks up on the last term, and of course it just gives us a current, right? And on the flip side, so I want to talk about how to differentiate the contraction of F mu nu with F mu nu, and so what I do is I rewrite it as the contraction of, these two guys against a pair of metric, Minkowski metrics, right? And so when I'm differentiating F alpha beta with respect to that means I'm differentiating this. But that gives me this like pair. So in order for to get non-zero, both the alpha and the mu have to match, and the nu and the beta have to match for this one. Or the mu has to match the beta, the alpha, and it has to match the nu, which is, that's this pair of Kronecker deltas. So that's how that differentiation's done. So when we calculate the derivative of the contraction of the field tensor, I first of all trade out these for the, I need to have the covariant field tensor, right? So like that. And I think what I'm doing is I'm going to chain rule, because let's see here what I do. So this is the derivative, this right here is the derivative of that with respect to that. That gives me this, right? And then over here I've got that is left alone, but I'm differentiating that, which gives me, again, this pair of, so I'm using the result up here like twofold, once here and once there, combined with the product rule, right? And you're like, well, why isn't that just zero? Because F is not A, and isn't the rule that when we differentiate with respect to the variable that's not exactly looking the same, doesn't that give us zero? And the answer is only sometimes, because it's specifically imposing independence of the potential and its derivative in this formalism. But we understand the field tensor is a function of the derivatives of the potential. These are ad hoc physics calculational principles that are hiding a deeper mathematics, right? There's a way of formalizing these things in terms of sections of fiber bundles and things, and like there's a deeper mathematics here to learn. But anyway, so you look at all that, you put these Kronecker deltas to work, and they freeze out certain sums and keep others. And after the dust settles, you've got 4 field tensors here. You notice that you got a mu nu, a minus nu mu, a plus mu nu, a minus nu mu. So they're all the same. So we get 4 copies of F mu nu. Hooray. So in short, this derivative, which was kind of scary, just works out to that. And so if you didn't know anything, right, and you just said, this is like F squared, right? This is like F squared. Well, so the derivative of F squared is, well, that's not quite F squared. I guess it's what? I guess that's the thing. Well, so the derivative of F squared is 4F. So it's not, it's kind of, sort of like what you'd naively expect, but that 4 maybe you wouldn't have seen coming depending on the notation you picked, I guess, right? Although, no, look, there's the 4 I'm wrong. There's a 4th up here, right? Well, anyway, that's why that 4th has to be there. The long and short of it is, like, where did the 4th come from to start with? The 4th came from model building. Where's the Lagrangian coming from? I just wrote it down. Where does it come from? Well, what's that? The variational. But the variational principle doesn't tell you what the Lagrangian is. It just tells you what to do with it, right? Or unless there's a deeper variation of principle that derives Lagrangians, which, I mean, I don't know what you guys did in classical mechanics. I'm learning things, so I don't want to state with authority. I don't want to state with authority what can't be done. I just know, so I can tell you the origin story for this Lagrangian. It goes back to 1919, maybe 1929. There's a paper by Weil, and he showed that if you think about a complex scalar field theory, complex scalar field theory naturally has a phase, a U1 copy of U1, unitary one by a complex number that has length 1, right, on the unit circle, e to the I theta, basically. And so if you look at the equations of complex scalar theory, you can basically multiply the complex scalar and its conjugate by e to the I theta and e to the minus I theta, and because the formulas for the Lagrangian, the things that construct the equations of motion, they're all quadratic, and they all compared with like a phi and a phi star. So you see, if you multiply the phi by e to the I theta and you multiply the phi star by e to the minus I theta, it conspires so that the e to the I theta and e to the minus I theta, they cancel out. So there's a symmetry of the original Lagrangian with respect to this global U1 phase transformation. So Weil had the idea that that wasn't quite right. It should be localized because physics is local, right? And so if you say that that theta shouldn't be just a global thing, it should be a function of space-time. When you do that, you face the fact that as you work through the Lagrangian, the variational principle for the scalar field theory, you find that you need to add terms to compensate for the variation of that variable phase term. And so that makes you change the derivative to what we call the covariant derivative. So that kind of motivates the existence of the four potential through these kinds of arguments. And then once you've done that, then you're faced with the question of, well, wait a minute, what about the equations of motion that govern the four potential for itself? Because the four potential is dynamical. So what are the equations of motion for the four potential? And then this is kind of like the simplest thing you could write down that would govern the motion of the four potential, is the contraction of the field tensor. And this is the argument by naturalness that you'll find in classic field theory books like this book by Ryder. This was kind of like the standard quantum field theory book for a while. And the argument I'm describing is in Ryder here, and it's apparently due to Weil, like I said, Weil. I mean, Weil, he proposed thinking of electromagnetism as what we would now call U1 gauge theory in 1919, but he was thinking of it perhaps he was thinking of the gauge symmetries maybe as too physical, like they're spatial symmetries, but they're actually more like mathematical symmetries of the theory. They're what we would now call an internal symmetry. And because he was thinking of them externally, as I understand it, Einstein basically said, what you're doing doesn't make sense because blah, 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 blah. He had like a pretty unassailable counter argument for his original 1919 work. So he's like, basically Einstein's like, go back to being a mathematician, you're good at that. There's some quotes like this. But then in 1929, Weil redid it, he had some kind of breakthrough in terms of his thinking about it. I don't quite understand the exact, these things are well documented in books and stuff, but so that this argument by sort of naturalness to discover electromagnetism as a variational problem in some sense goes back to Weil, 1929. It's a precursor to the more general variational calculus, and like if you replace the U1 gauge group with an SU2 gauge group or an SU3 gauge group, that leads us to like electroweak physics or the physics of the strong force at the classical level. So like the standard model physics is all at a classical level, classical field theory with gauge groups that are like SU2 or SU3, things like this. But this is the first step in that story, is thinking of electromagnetism as a gauge theory. And but anyway, so there you go. I mean, Lagrange equations give us the non-homogeneous Maxwell equations, right? So I think what's going to happen for you guys, and the problem I assigned you, is like everything that happened with the F mu nu, that should be boilerplate the same as what happened here, right? But the derivative of the Lagrangian with respect to the fields, well, when you have that MAA term, I think you're going to pick up one more term here with maybe plus M times A or something like that. I think that's the answer. I'm not sure, but it should be pretty straightforward to track this. And, sorry, swimming update. And I know Sam will want to see, Sam's always interested in the stress energy tensor. Here's the stress energy tensor for the scalar field. Oh. And here is the stress energy tensor built from the field tensor. We hadn't talked about that yet. And so there it is, though, in gory detail. You can build the stress energy tensor from those. And that, of course, is important if you study general relativity, because the general relativity, Einstein's equations are built using the stress energy tensor. So this is what I was just talking about. I think this is a fitting place for us to more or less end this semester is, electromagnetism is just the first step in discovering a deeper category of physics, really, that if we have a local symmetry, some kind of local symmetry, and we adjoin a gauge field to describe the dynamics of how that local symmetry is propagated, this leads us to electromagnetism. If the gauge group is U1, but if the gauge group is, so like SU2, and there's a more complicated business because there's something called electroweak symmetry breaking. Actually, SU2 physics comes from, at a higher energy, there's, I think, I'm trying to remember I don't remember the words, but I believe at the higher energy they're all massive, like the gauge bosons are massive. And what that means is that the reason that electromagnetism has infinite range in part is that the mass of the photon is 0, right? If you go before the electroweak symmetry breaking, the unified force has force-carrying particles which are massive, so it's more short range. Somehow in the symmetry breaking, some of the particles change to acquire mass, and then the photon becomes massless. The ones that acquire mass are the W plus minus and the Z current, I think, of electroweak theory. And of course the photon, as we know, is massless. So there's that. Now, I don't know nearly, I just know just a smidgen about that. But, what I can tell you about like chromodynamics and all that, I don't know too much. But there's so much that's known at this point. Like all of the standard model physics is in some sense or another based on these ideas at the lowest level. But there's a lot more, like in the quantum field theory in terms of renormalization and how quantum mechanics goes together with all of this. Opinions vary. Physicists will say that quantum field theory is done. Mathematicians will say no, not even remotely. You don't know what you're doing yet, really, because this process of renormalization involves something like there are terms in the physics which are divergent. So what do you deal with what do you do when you have a divergence? When you have something going to infinity in your physics, what do? You just do what? You just kind of work around it, right? So like this renormalization process, the way I've heard it described, is something like they just kind of absorb the infinities into these constants somehow or another, and then it's not you'll hear people say things like this: the quantum field theory is not really physical until after renormalization. So they would say, some person like that would say, all this classical field theory is not really physical because it's not been renormalized, and all of the physics is in the renormalization. That's where you're making contact with measurement and so forth. And I don't know what all that means. I just know that people who know more have said that it'll be another 50 to 100 years before the mathematics of quantum field theory is properly done. So there's a lot of like very sketchy mathematics in the quantum field theory, like if you get deeper into it. But anyway, I have another talk I can show you guys about why we do believe in quarks like that is understandable. I don't think I ever showed you that, Jared, did I? I know you've seen it, Shane, yeah. But if you don't mind, I'll load that up. So I can find it. And then we'll be done. So I know I'm being like pretty fuzzy about what I mean by gauge theory, and that's intentional on my part. But there is, like, classical gauge theory at this point is a pretty well-defined project. There's, books on it, and you can read tons of well-written things on this. And it's a very interesting story in the sense that the gauge theory was discovered by physicists like Yang-Mills theory. Yang just died, actually. He was 104. But Yang and Mills in like 53, maybe 57, I can't remember. They come up with what's called Yang-Mills theory. But what that was they generalized electromagnetism to a U1, SU2 gauge group. About the same time, there's a Japanese fellow named Udiyama who did it for an arbitrary gauge group. So that was in the mid-50s. They came up with gauge theory for like an arbitrary gauge group. But it was thought to just be sort of a theoretical curiosity, right? It wasn't until like the early 70s when Tufte and Glasgow, Weinberg, a few others, they put this stuff together to create the electroweak theory with the symmetry breaking. And then all of a sudden, like, they'd explained some things that's pretty neat. You've got a story about weak physics and electricity and magnetism as part of a unified story. Like, that's interesting. And so, like, interest in Yang-Mills theory, of course, took off around that time period. So around the early 70s, it was just sort of this grab bag of, these are the rules, this is how you calculate it. The gauge field has to transform this way under the gauge transformation, right? But there's these sort of ad hoc rules that were made in order to maintain the invariance of the Lagrangian under the local gauge transformation. So these were just kind of a storybook that physicists came up with, and it was consistent. This is how physicists operate, right? Around the same time period, mathematicians were working on things called vector bundles and connections on fiber bundles. And it was about in the early 70s where all of a sudden they realized, oh, it's the same mathematics. Because the rules for how a section on a fiber bundle pulls back to the base space, if you look at two different choices of gauge group, two different sections, if you will, when you compare those on the base space, that's the transformation law which was demanded by physicists. So my advisor actually understood this before a lot of people, and he remembers in the early 70s they had some like postdocs from Princeton visiting, and they were like, wait a minute, it's what? He's like, yeah, doesn't everyone know this? And no. So he's like, for a moment, he was at the edge of things, And then theoretical physics has a habit of reinventing itself. And string theory happened. But anyway, so quantum mechanics basically is, you have wave functions, you have a Hamiltonian, right? And a symmetry of the Hamiltonian is something that commutes, right, the commutator of the Hamiltonian with that symmetry operator. If that commutes, well, then that's a symmetry of the Hamiltonian. And so, in a nutshell, if you look at the proton and the neutron, they have very similar mass, right? So it suggests, anytime there's similar mass, that suggests there's an underlying symmetry. General principle of field theory. And so protons and neutrons were thought to have an underlying symmetry called isospin symmetry. And also, when you look at those, the pi mesons, so protons spin up, neutron spin down, isospin 1/2 both. They form what's called an isodoublet. If you look at the pi plus, pi minus, pi 0, this forms an isotriplet. These things, this is all from like nuclear physics in the first half of the 20th century, 21st century. 20th century, we're not doing, wait a minute, no, 20th century, I can't count. Anyway, so here's some like, high energy at the time, now nuclear reactions, right? The high energy of yesteryear is the nuclear of today. But, so like, these are different processes that were observed. And if you study particles in, particles out, you can start to see, oh, there's something called isospin that's being conserved in these processes. And then, so the pions are apparently different representations, as they're known, of isospin. So somebody had the bright idea of introducing then something called hypercharge, which is based on the isospin and also the regular just charge. So charge is Q, but the hypercharge is Y, which is some newfangled thing we're just introducing. And if you do that, then you can see that the neutron and the proton doublet have hypercharge 1, whereas the pion triplet has hypercharge 0. All right, so hypercharge labels these multiplets of states. And so this is the Gelman-Nijima, I can't say it right, relation. And this is all very cool. It was what we used to call the particle zoo, which was this plethora of high energy particles we discovered with, like earliest 20th century particle colliders and stuff. And if you arrange them according to isospin and hypercharge, all of a sudden you start seeing all these patterns. Like where is this structure coming from? Why are the particles arranged like this, right? And so this is probably the height of that story, was in 1961, Gelman noticed that you've got all of the things in red, but this is missing. It just like screams at you, there's something here, right? And so he predicted that they could find a particle with these properties in 61, and in 64, they actually found it. Wouldn't that be amazing to like predict a particle and then within your lifetime, not just within your lifetime, like by the time you've got the paper published, like somebody finds it. It's amazing. Very exciting. But then the question is, where are these patterns coming from? Why? Why are there these patterns in isospin and hypercharge? And there the answer actually rests in what's known as representation theory of SU3. So SU3 is the special unitary, the gauge group, not gauge group, matrix group SU3 is 3 by 3 unitary matrices with determinant 1. Little SU3 is the Lie algebra of that, which is the tangent space of the identity, whatever. Anyway, those are the matrices that are in there. And so, long story short, there's actually 3 copies of isospin in that. There's a T, a U, and a V sort of isospin inside there. And there's all this algebra. And so you can see how these things act on the iso states, the hypercharge and the isospin states. And like what they do is these different operators in the SU3 algebra either go that way or this way or that way or this way. So once you have those ways of moving the states, you can see how you generate the pictures that we just did. So getting to the point here, this is some inside baseball for us. We go on here. So the quarks are what are known as the fundamental representations of SU3. You have an up quark, down quark, strange quark, and their anti-quark pairs. And if you put those things together, you can build particles that have net properties, which are built from the sum of the properties of the quarks that comprise them. Like the hypercharge and the isospin of the constituent quarks leads to the net hypercharge and isospin of the the particles they construct. And it just turns out that you get fractional charge for the quarks, which is a problem in terms of observation, because there has never been the observation of anything but an integer multiple of the electron charge. This has been tested to stupidly accurate. I mean, it's a very well experimented problem. And so in a nutshell, if we have 2 quarks, we can put them together in all these different ways. And if you do that in all these different ways, you can construct the particle zoo by understanding that those particles are built from quarks. And if you then add 3 quarks together, you can build these. So mesons are integer spin, I think. If you let's see here, put 2 quarks together. Here's how, as I said. And if you put baryons or fermions, like protons and neutrons. And if you put 3 quarks together, and you can view it geometrically like I have on these slides, then you get these different up and down quark pairs. And we can then predict the properties of all of those particles in the particle zoo. We can understand all of those different particles as being constructed from these constituent quarks, including the proton and the neutron. All of these other things, in some sense or another, they're sort of high energy excitations of like the proton or the neutron, like very crudely speaking. So that's why we think there's such a thing as quarks. Pretty much, because these pictures are very convincing. I mean, it would be an incredible coincidence for all of these particles to exist as they do and have the properties they do if there wasn't something inside them like a quark. But quarks have never been observed on their lonesome, right? They have fractional charge. You can't just observe them. And then, so this is all just the, this is all just phenomenological, right? This is just storytelling, really. Like, all of this is not coming from like solving the Lagrangian and finding equations and solving them. Like, none of that is happening here. In fact, so there's the SU3 that's part of like quantum chromodynamics, the basic field theory of these things. No one, as far as I know, it's an open problem to actually find equations which behave as the quarks. Like no one, as far as I know, like bound states of SU3 like that would behave as quarks, that's an open problem. Actually, so like we think there is such a thing, but we don't actually know how to produce that from the underlying field theory. So there's like different things we have in modern physics that we hold with varying degrees of certainty. It's still very much an open project. Sometimes you don't get that feeling listening to some physicists, you know. You get the feeling, well, we found everything. There's nothing more to find. The standard model's done. Well, maybe to a physicist, but certainly not to a mathematician. So anyway, that's a pretty good place to stop. So I hope you guys enjoy the test. Any questions?
That's also what they thought before quantum mechanics is all, I think. But
Yes. Quantum mechanics is, I wish I understood it.